Hi everyone, and welcome to the first joint design log. Building a humanoid robot that fits real human proportions means no compromises on compactness. Every joint, every actuator, every structural element has to fit inside the actual volume envelope of a human body. Today we're documenting our lower leg assembly, from footplate to knee interface, with primary focus on the ankle joint. The ankle is the most constrained joint in the leg, which makes it an ideal test case for our design strategy. It has the tightest volumetric restrictions. The ankle itself has a limited diameter, around 60 millimeters at its widest point to match human anatomical proportions. But the constraint doesn't stop there. The lower leg, the shin and calf region, also has to house the motors that drive the ankle. The calf diameter is around 110 to 120 millimeters, which leaves a very narrow working envelope for motor positioning, structural elements, and routing systems. A tendon-driven actuation strategy, where motors are mounted remotely in the shin instead of directly at the joint, is the only approach we found that satisfies these volumetric constraints. It's bio-inspired. Biological legs work the same way, with muscles in the calf transmitting force to the foot through tendons. This architecture allows us to keep the ankle joint compact while maintaining adequate torque output. The ankle has 2 degrees of freedom, plantarflexion and dorsiflexion in one axis, inversion and eversion in the other, which significantly complicates the mechanical coordination. Managing multi-axis motion with coupled tendons is a control challenge we're working through. If we can solve the ankle, the same principles apply to other joints in the leg. This is joint design log number 1. The ankle joint has 2 degrees of freedom, with both rotation axes intersecting at a common center point. This is critical for keeping the joint compact. If the rotation centers were offset, it would significantly complicate the mapping between motor angles and joint angles, requiring more complex control algorithms. The first degree of freedom is plantarflexion and dorsiflexion. That's your foot pointing down and pulling up. Plantarflexion goes to minus 50 degrees, dorsiflexion to plus 25 degrees. The second degree of freedom is inversion and eversion, the foot rotating inward and outward. This gives us plus or minus 25 degrees. We designed for 2 degrees of freedom rather than 3. There is a third rotational axis in the human ankle, axial rotation around the long axis of the shin, but it's significantly smaller in magnitude compared to plantarflexion or inversion. We're validating dynamic performance now, making sure the joint can move smoothly through these angles under load and at the speeds required for natural-looking locomotion. Actuation is tendon-driven with 4 motors total, 2 per degree of freedom. Each pair works as an antagonistic configuration. One motor acts as the agonist, pulling to create motion in one direction, while the other acts as the antagonist, controlling the return motion. 3 of the 4 motors are identical, but the plantarflexion motor is larger. It's designed to provide higher torque output because that motion requires more force during the push-off phase of walking, when the foot propels the body forward. The motors also counter-rotate to cancel angular momentum, which is critical for maintaining balance during dynamic motion. Each motor has an integrated planetary gearbox, providing a 10-to-1 reduction. On top of that, we use differential pulley diameters at the motor output and joint input to gain an additional 5 to 7 times mechanical advantage through the tendon transmission. Total reduction works out to around 1 to 50 to 1 to 67, depending on the degree of freedom. This gives us adequate torque for a lightweight humanoid without requiring massive motors. The antagonistic configuration also provides control benefits beyond just bidirectional motion. By varying how much tension both motors apply simultaneously, what's called co-contraction, we can modulate the joint's stiffness. High co-contraction makes the ankle rigid, which is useful for maintaining support during the stance phase when the full body weight is on that foot. Low co-contraction makes it compliant, which helps absorb impacts and adapt to uneven terrain. This variable impedance control is something we'll validate more thoroughly in future testing, but it's a significant advantage of this architecture. We're also planning an external shell that matches human anatomical dimensions. This would enclose the foot, ankle, and lower leg structure, with plans to extend it to the full leg in future revisions. The biggest challenge there is managing material deformation at the joints. The shell needs to stretch and compress as the ankle flexes through its full range of motion without restricting movement or creating binding points. That's a non-trivial design problem we're working through. Phase 1, targeted around 6 months from now, is when we'll open the full CAD files under a Creative Commons Share Alike license. That enables community contributions and anyone who wants to build their own version. For now, this is Phase 0. Validate the mechanics, document honestly. Repository and updates linked in the description. This is Joint Design Log number 1. Thanks for watching.